This is the last of 3 videos on the pentose phosphate pathway. In the first 2, I looked at the non-oxidative part of the pathway and then the oxidative part. And today we're going to talk about how those integrate to let cells make different things at different times. So if you haven't watched those videos, you might check them out. Otherwise, let's just launch into this. So this is modes of the pentose phosphate pathway. So again, orient ourselves in metabolism. We've been talking overall about things like glycolysis and glycogen metabolism. Right now, we're focusing right up here in this pentose phosphate pathway network. There's 2 chunks of this. There's the non-oxidative part, which involves metabolites that swap around. You have like G3Ps that become F6Ps and R5Ps becoming Ru5Ps, etc. And then that is adjacent to this oxidative arm. And that oxidative arm generates NADPH. So we have basically these 2 things collaborate together to generally make things that are useful as feedstocks to go on and build other molecules in metabolism. It's a responsive network of reactions. What that means is that all of these reactions here are fast and reversible. So as you change the concentrations of these molecules, because of, let's say you're doing a lot of nucleic acid synthesis, and that means you're depleting Ru5P, the whole network will respond by molecules flowing towards Ru5P. Because everything's fast, it can just respond and quickly go that way. This makes it an extraordinarily flexible little machine inside of metabolism when we, have different metabolic needs that we're approaching. I wanted to illustrate this in a way that I don't know if it's helpful, but for me it was cool as I was really digging into the pentose phosphate network. So what I did is I wrote out a mathematical model of the pentose phosphate pathway. Details are not terribly important, but if you are a nerd, this is what's known as a Gillespie simulation, which is a stochastic simulation of a metabolic network. And what I basically did is I started with 1,000 G6Ps, no other molecules, and no NADPH+, and then I just let the reaction go. And I ask what sorts of things accumulate. So it's a little bit small, so I'll zoom in here. But what I'm showing here are different molecules. So we started out with a lot of glucose 6-phosphate, right? That glucose 6-phosphate concentration is in blue. It starts to go down. Then we see things like fructose 6-phosphate accumulate, and then all the other molecules in glycolysis reach some kind of steady state level. And then if we look at the pentose phosphate pathway, at least in my very simple implementation of it, it turns out that S7P ends up being the most dominant molecule. Now, don't take that as a real finding, right? I'm not saying S7P is the highest concentration molecule in this network. This is basically a rough model of a network that has this sort of architecture so that we can see how it changes as we change the input. So the idea is not this is what the network really looks like. This is how a network like this behaves, right? As you add a certain number of substrates, you see different outcomes coming out. Okay, so I ran that simulation with no NADP+. What if I add NADP+ to the simulation? Hopefully what you see is it just looks different, if nothing else. So when I start with 1,000 NADP+ molecules in here, we see a different configuration come out. We basically don't ever see a spike in fructose 6-phosphate. Instead, we end up populating a heck of a lot of, let's get the numbers right. Sorry. We get a lot of 1,3-BPG, for example. And then over here, we get a spike in Ru5P rather than just a simple accumulation of S7P. And the idea here is just by changing which substrates are around, because of how this is built into this network, you can just get completely different outcomes just by changing the concentrations of stuff, which is cool because most metabolic networks don't really behave like that, right? They have all this regulatory schema on top of it. This is just Le Chatelier's principle applied all over the place. Okay, what this means is that the pentose phosphate pathway can actually operate in different modes that depend on different cellular needs. And what I'd like to do in this video is go through 4 of these modes and talk about how cells can use it. So we can sort of see the flexibility of this metabolic network. And so I'm going to show 4 different situations. And for each one, I'd like to ask 3 or 4 questions, basically. For every G6P that we throw in, glucose 6-phosphate, what is the production or consumption of NADPH, so reducing power, remember? Ru5P, a metabolic intermediate that goes on to, make nucleic acids. ATP, are we consuming ATP or are we making ATP? And then finally, we can talk about under what conditions this might be active. Now, when I teach in a classroom, I actually have a worksheet and I have students do this sort of on the, as groups or on the fly. I actually have different, I give the mode to different class people and they present it. We can't do that in this video, but if you'd like, when I come show each mode, you can rapidly hit pause and then say, all right, what's happening? Am I making or breaking NADPH, R5P, et cetera, yourself before I talk about it? So, all right, let's dig into these. So here's one of the modes. And what's happening in this mode is we are taking F6P and we are converting to G3P into R5P. And that R5P is then going into anabolism, right? So we're going, just to walk through this, we've got a glucose 6-phosphate. If we put a tracer on there, we followed it, what we'd see is some of the time it goes to Ru5P, some of the time it goes through glycolysis and then gets kicked out as Ru5P. So we're basically making R5P and sticking it into metabolism. All right. So given what we know about this pentose phosphate pathway, what's happening to each of these metabolites? Now we're not running oxidative pentose phosphate pathway, right? I don't show G6P going to Ru5P, that irreversible oxidative arm. So we're not making or doing anything with NADPH. R5P, turns out R5P is going up, right? We're making lots of R5P, and we're making it by both arms here, by fructose 6-phosphate and glucose 3-phosphate can be filled into that. What about ATP? Are we using it? Are we consuming it? This is a little bit subtle. You have to know your glycolysis well, but it turns out we're using a small amount of ATP. And the reason is here, this step going from fructose 6-phosphate to fructose 1,6-bisphosphate. You'll notice we went from 1-phosphate to 2. That's because this reaction takes an ATP and makes an ADP. So we are, in fact, consuming a little bit of energy here. So what is this used for? Well, this is used for max R5P production. If you want to invest basically every carbon that comes in G6-3, 6P into Ru5P, this is the way you run this engine. So this might be happening if you are just duplicating your genome. That's all you're doing. You need as much R5P as possible. This is the way to run this network. Okay, cool. Let's go into our next one. Now I'll summarize these all at the end. Next one, what we're going to do is we're going to oxidize G6P into R5P. And then we're going to feed R5P into anabolism. So what are we doing here? We're running the oxidative PPP. And then we're taking that oxidative PPP and we're generating R5P, which they can go on to make stuff. All right, so what's going on here? NADPH, we are going up, right? We're making NADPH as part of this process. R5P, also going up. We are making R5P. But not as much as the last one, right? We're kicking off carbon dioxide here. Some of our carbons are being devoted to NADPH, not to R5P. ATP, turns out we're not actually using any at all. And so what is this useful for? Well, this configuration of the network is a mix of reducing and R5P production. Should have said power. There we go. So we're making NADPH to make reducing power. We're making R5P. This is actually a really good configuration you might have when you're, say, duplicating a cell. Because when you're duplicating a cell, replicating, what do you need? Well, you need to make your entire genome again. So that's going to mean you have to make a ton of nucleic acids. You're also going to have to make a bunch of fatty acids, right? Because you have to duplicate your whole membrane. So you're going to need a mix of reducing power and of R5P. So this is, maybe more plausible than all of your resources being devoted solely to making R5P. You use some of your resources to make R5P, some of your resources to make reducing power to make fats. All right, let's talk about mode, I guess it's labeled as 4, but mode 3. So this looks really complicated. What's going on here? Well, what we're doing is we're oxidizing G6P to R5P. So we're running the oxidative pentose phosphate pathway. And then we're taking that R5P, and instead of feeding it into anabolism, we are feeding it into glycolysis. It can enter, because of the way the pentose phosphate network works, it can enter as both F6P or as G3P. Okay, so what are we doing with this? We're making some NADPH. Cool. Are we making R5P? We're not really, right? We're not making anything that's going to go on into or it's like be used to say make nucleic acids. Instead, we're just using it right away. Instead, what we're doing is we're making ATP, right? So we have to invest in ATP and not there. We have to invest in ATP there, sure. But this is glycolysis, right? For every F6P we put in or every G3P we put in, basically for every 3 carbon unit, we're going to get out 2 ATP. So this is a net energy generating pathway. And then if this goes on to say oxidative phosphorylation, we're going to get a ton more ATPs out. So what is this used for? Well, when might you want to make ATP and NADPH? This might be a scenario, another sort of growth scenario, right? This is sort of living in, say, a low ox environment. So sorry, I'm going to say that again, an oxidative stress. Wow, I cannot write environment. Okay. And so this actually is an example of the sort of thing that a cancer cell might be doing, right? So they need to make NADPH to deal with, say, oxidative stress. They also need to get some energy out, and so they're going to run this pathway to sort of take their carbons and both make NADPH and make some ATP. All right, last one, and then we will summarize these. In this one, what's happening is we're going to oxidize G6P to R5P. So we're going to run this thingy. And then we are going to take R5P and we're going to turn it into glucose 6-phosphate. So we're going to feed back through the network to generate R5P. And the question is, what's this doing to our stores of all these molecules? So NADPH, it has given us a lot, right? We're running this over and over and over again. In fact, we're going to get 12 NADPHs for every G6P if you run this network like this. R5P, we're not making any. ATP, we're not making any. What is this doing for? This is max reducing power. This would be a cell that all they need is to deal with, say, oxidative stress in the environment. So they're just making a ton of NADPH, and they're doing it by completely recycling every every R5P goes back into G6P. And so what we can think about is these are making this up go away, 4 different ways you might operate the network. These aren't really like explicit categories, right? You can think about these as different poles. Like if you put the network in this configuration, it'll look like this, but it sort of can slide amongst all of these, right? So you can make maximum anabolic precursors, which would be use G6P and ATP to make the non-oxidative PPP run as much as possible. You can make a mixture of anabolic precursors and NADPH. So in this case, you're taking G6P and you're feeding it into oxidative PPP and then putting that into R5P. You can do a blend of NADPH and energy production, right? You can take G6P and make it into R5P, but then throw R5P into glycolysis. Or you could just run maximum NADPH, which is just take every G6P, run it back into R5P. Run the R5P back into G6P. And so, again, these are different configurations, different possible configurations. And what a particular cell doing is at a particular time is going to be somewhere around, it's going to be sort of wandering between these depending on the exact current metabolic needs of the cell. And this is why, if you ask me what is my favorite metabolic pathway, this is it. Because what you have is this really cool network of reactions that gives metabolic flexibility, right? We're not just, running, you start at G6P and you get out, pyruvate at the end and glycolysis, yay. You have this network that depending on, if you're making nucleic acids, it's doing something different than if you're making amino acids. And then if you really need a lot of energy and you need to dump things into glycolysis, or you're really dealing with oxidative stress, this is what's kicked off. All based on Le Chatelier's principle Le Chatelier's principle writ large. I keep ending with this slide actually, but this is actually a good example of this is in cancer cells. Because cancer cells, they don't have a completely new metabolism, right? They just take an existing metabolism and they shift it that way. They're doing something different than normal cells, and one of the observations is they're going to kick up the PPP to deal with oxidative stress and make the metabolites they need. All right, so that is the end of our tour of the pentose phosphate pathway. Hope it was interesting. Hope that it is now your favorite metabolic pathway. Thanks for your time, and I will see you later.